Okay, so yesterday we were talking about inclined planes. And we talked a little bit about kind of the geometry behind where these two equations come from, right? There's two equations here, we just can't see them both. We talked a little bit about the geometry behind where these two equations come from. Okay. But I feel like in going through that geometry, what got lost was how to solve the problems. Okay? So I want to rewind and show you how to do inclined plane problems again. We're going to do, I think, 2 problems. Alright? I'll try to do them as quickly as we can so you guys have some time in class to work on them. Okay? 6th hour, they had about 20 minutes, but they also had a longer period. So, alright, so here we go. So when you're given a problem like this, where you've got an object on an inclined plane, step 1 is the same as any other problem, which is start by finding your force of gravity. Alright? The one catch is this. We're not going to draw the force of gravity. Okay? So here's what we're going to do. We got a 40 kilogram box. So your force of gravity would just be 40 times negative 9.8. So you get negative 392 newtons. Pretty good up there? All right, now, so the idea is, don't draw this, but so gravity pulls down this way, right? But remember, yesterday we talked about this idea that what we want to do is we're going to rotate our axes system so that we've got this parallel axis and this perpendicular axis, right? So in terms of doing our calculations, what we're going to be interested in is not the force of gravity, but rather the two components. All right? So when you're given an inclined plane problem, start by finding your force of gravity, then find your two components. All right? So remember, force of gravity perpendicular is just Fg times the cosine of theta. So for us, that's going to be negative 392 times the cosine of 30 degrees, right? And so that gives you negative 239. 339. Is that right? Oh, 330. Thank you guys, by the way, for being quiet. My voice is struggling. All right? And then similarly, well, so let's draw it. So that's our perpendicular component. So that's going to go down here. Fg perpendicular is negative 339 newtons. Cool? All right. And then similarly, we can find our parallel component. The parallel component will always be Fg times the sine of your angle, which is negative 392 newtons times the sine of 30 degrees. So that just gives you negative 196. Put that on the drawing. This is all stuff we've done yesterday, but I felt like this drawing kind of got rushed and lost in the mix. So we all okay up to there. Right. A quick side note. Ideally, I would love for you guys to understand the geometry for where these two equations come from, but realistically, it's not going to matter. Okay, as long as you remember that these are the two equations, to find those components, you're in good shape. All right? If you take AP, it'll be more important to understand where those come from. But for now, I think you're good. Yeah, Seth.
Will theta always be given?
Or that's what you'll be looking for. So, a quick note about that, though. When you do this, I just said that these are always your equations. That's assuming that theta rather is measured off of the horizontal. Okay. All right. Everybody good? Okay, cool. What force am I missing on my drawing? Normal force, right? So point for me. What direction does the normal force go in, you guys? Opposite the perpendicular component, right? It's going to go this way, right? All right, and then how big does it have to be? It's got to be big enough so that the two perpendicular forces cancel, right? Because all of our motion is in the parallel axis, right? There's no motion either up away from the ramp or down through the ramp. So this has got to be positive 339 newtons to cancel out this dude, right? All right, cool. So now that we've got all that, we can find our acceleration. So acceleration is net force over mass. So our net force here, well, the perpendicular forces cancel, so our net force is just negative 196. All right? divide that by the mass of 40 kilograms, and you end up getting negative 4.9 meters a second squared. Choose. Josh, you just said, I just realized something. Before, so what you just realized? Yeah, so it turns out I did the same problem with my AP class the other day, except I didn't give them the mass of the box. Turns out the mass of the box doesn't matter because all of these numbers are dependent on the mass, and so the mass ends up canceling. There's an equation that if you're looking at an object on an inclined plane and there's no friction, then the acceleration of the object is just ag times the sine of the angle. So sine of 30 is a half, right? And that's because this parallel component, whereas depends on the sine of theta. So basically, if you divide both sides of this by mass, you get that. All right, so are we good? All right. Now, when you make your free body diagram, so I'm trying to remember, right? So I took, whatever, first year physics when I was at U of M. I don't remember ever having to sort of draw these technical free body diagrams. And I don't know if in the last 20 years people have been like, we need to make kids draw more free body diagrams or what. But it seems like it's a bigger thing now. So when you make your free body diagram, you don't draw the components, you just draw the actual force. All right, so if I wanted to make the corresponding free body diagram for this situation, here's what you would do. Do I have one more blank page? Where's my thing? Let's do this. So here's what your free body diagram would look like. You draw your object. Technically, you're supposed to just draw a dot, so I'll actually do that. All right. Drawing your coordinate system. And then identify your forces. So, force of gravity is negative, what was it, 392? And I know that this angle here is 30 degrees because it's the same as the angle of the ramp. And then what other force is there, you guys?
Normal force.
Normal force, which was 339. And that's it. That's your free body diagram. So what I did is I replaced, the two components with just the force of gravity. All right, so this is what the free body diagram looks like, but it's sort of not helpful, right? Because you can't look at this and know that there's no motion along the perpendicular axis, right? So I kind of don't see the value of that. To me, in terms of problem solving and understanding what the object is doing, this holds way more value. So anyway, that's the deal with it. Cool? Any questions? Yeah. Oh, yeah, I'm sorry. Happy? I don't know, it's a couple of weeks ago. They were here on home, well, the dinner lunchtime. They're here at homecoming, and they're like, "You need some decorations in your room." This was before all the ducks. So they bought me those for my birthday. Okay, everybody good? All right. All right. So this one's kind of more of the same thing, except this time we got to deal with friction. All right. So we got a 30 kilogram box sliding at 6.5 meters a second, which is sliding along, and then it begins going up an inclined ramp, an inclined plane. The plane is inclined at 25 degrees. You're given your coefficients of friction, 0.5 and 0.4. A wants to know how far the box is going to get up the ramp before it stops. Okay. So let's start by making a drawing. So you need a ramp, you need a box. I guess I can label my mass, 30 kilograms. All right. What's the first thing we should do?
Force of gravity.
Find that force of gravity, right? So my force of gravity is going to be 30 times 9.8, which gives you negative 294 newtons. Now what? we need the two components, right? Right? Because gravity points straight down. That's not going to sort of lie along my parallel or perpendicular axis, right? So I need to find my components. So let's go over here and do that. FG parallel is going to be negative 294 times the sine of, is it 25 degrees? I guess I could look. I'm holding this paper in my hands. And so that gives you negative 124.25 newtons. And my perpendicular component is going to be negative 294 times the cosine of 25 degrees. And that gives you negative 266.45. I've tried to make that green so it's not so thick and it doesn't stick. So I don't know why it does that. All right, so let's put those in our drawing. Let's see. So we've got FG perpendicular, we just decided was negative 266.45. Remember, you guys, I'm keeping some insignificant digits, and then I'll round at the end, right? All right, so we've got FG parallel. When you write down your force for FG parallel, draw it, like, put your force at the bottom, and label it underneath. There's going to be another force here, so I'm just leaving myself room to draw another force, you know what I mean, and label it. Everybody good? Right. There's one other force I can do without really doing too much calculating or thinking or anything. I'll get to kinetic friction in a second. I can't find kinetic friction though without finding something else. Normal force, right? So let's put in our normal force. It's got to be 266, right? So if you guys want to write this down, you may. For the purposes of this course, if you've got an object on an inclined plane, the normal force will always be exactly the same as your perpendicular component. All right? Because in this class, if there are any other forces, they'll be parallel to the ramp, not at a weird angle or anything. Okay? In AP, we're doing stuff like you push a lawnmower up a ramp, you know, and then you've got this other force, and that's sort of one extra step of difficulty. But everybody good up to there? Yeah, Zach.
So if the angle exceeds 45 degrees, then does the parallel and the perpendicular force change?
No, if the angle's, well, so if the angle is less than 45 degrees, then the parallel component's smaller than the perpendicular. But as you get closer to 45 degrees, they sort of switch places. You know what I mean? So, cool. So if you're more than 45 degrees, the parallel's more than the perpendicular. Good? Everybody good? Okay. All right. What should I do next? Friction, right? What kind of friction do I want? Kinetic, right? Because the box is sliding until it stops, right? So everything in this problem is going to be about kinetic friction. So my force of friction kinetic is going to be my coefficient of kinetic friction times my normal force, which for me, what was the coefficient? Was it 0.25? 0.4? What? Oh, I found the wrong problem. Thank you. Times my normal force of 266.45 gives me, where did I put my papers? 106.58. All right, now, point for me. Which way is the kinetic friction going to go? Okay, I see some people pointing up, some people pointing down. So if you read the problem, it says, how far will the box slide up the ramp before stopping? So because the box is going uphill, friction is downhill. So there are actually two forces slowing the box down. Gravity and friction. Cool? What I didn't do that I probably should have done is I should have done this. Oops. Cool? Because now that shows me the velocity's uphill, which means friction's got to be downhill. This is like the cake problem from the test the other day. Except that wasn't on an inclined plane. Are we good? All right, so now what? Yeah, are there any other forces? No, there's nothing pushing the box up the ramp. It's just sliding, right? If Roy was pushing, we'd have to include that in our drawing, but it doesn't say anything about anybody pushing it. It's just sliding. This is it, all right? So now we can find our net force. So the net force is the sum of all the forces. So for us, that's Fg perpendicular plus the normal force plus Fg parallel plus the force of friction kinetic. I think that's all four forces, isn't it? Right. Now, two of those forces I don't really need. Which two?
Normal.
Normal and perpendicular cancel, right? So my net force is really just going to be the negative 124.25 plus negative 106.58. So you get a net force of negative 230.83. So that's my net force. So to find the acceleration, I should take that number and divide it by the mass. The mass was what, 30? So you end up with an acceleration of negative 7.69 meters per second squared. All right. So we got one last thing we got to do. What's the last thing we got to do? We know the final velocity. Yeah, we got to figure out how far it goes before it stops, right? So here we go. We know that our starting velocity was 6.5 meters a second. We know our final velocity is going to be 0 because it's stopping. We just found our acceleration, and we're looking for our displacement. Oh, too far. All right, so somebody remind me, when we're done with the notes today, I want to put a list on the board of all the constant acceleration equations that we learned, just 27 chapters ago, that are going to come up a lot this chapter, so we need to make sure that we review them. All right, so the one that is going to help us here is this guy. Right, we know everything here except for your displacement. So find it, and it ends up being 2.48 meters. Is that right? Or 2.4? Oh, no, that's totally wrong. Don't write that down. 2.75, sorry. Cool? All right, so, questions about what we did there? Yeah, Molly.
When you draw the diagram, would you want us to draw the perpendicular component and the parallel component of force and gravity like I did?
It depends on what you're trying to do. If you're just trying to solve the problem, then yeah, I want you to draw perpendicular parallel separately.
Okay.
All right. If I ask you for a free body diagram, then you replace these two forces with one force of gravity. Cool. Are we good? Okay. Now, so what just happened? The box was sliding. There was nothing pushing it forwards. So both the parallel component of gravity and kinetic friction slowed the box down until it stopped, right? So the box went and stopped. So now what's happening is gravity's pulling it down the hill, but it may or may not move down, right? Because it's at rest right now. For a split second, it's at rest. And now we need to see if there's enough gravity to overcome the static friction to get it going back the other way. Does that make sense? All right. So question B says, will it slide back down? If so, how long does it take? If not, how much force does Roy need to make it slide back down in 1.5 seconds? So here we go. Part B. So here's our ramp. Here's our box. We've got a perpendicular component, which was negative 266.45 newtons. We've got a normal force that is the same thing. We've got a parallel component, which is negative 124.25 newtons. And right now our velocity is 0. So it may or may not get moving. If it stays at rest, what's the name of the force that's going to keep it at rest? Static friction, right? So we need to go over here and find that maximum static friction, right? And notice our normal force is 266. So, is it going to slide down the hill?
No.
Nope. So if it was that, if the problem just said will it move or not, make a free body diagram, you'd be done. Except you'd have to put in you'd have to put in your force of static friction, which would be 124, right? Enough to cancel it out, right? Molly? Oh, okay. All right. Is everybody good up to that? All right. So if Roy didn't touch it, it would just stop. Okay. But if you read the rest of it, it says, how much force should Roy use to make it slide back down in 1.5 seconds? So, we're now going to assume that it's actually going to move, and we got to figure out how much force Roy needs to make that all happen. So, here's what we know. We know that our starting velocity is 0. We know that, how far does it have to go to get back down the ramp? 2.75 meters, but negative because it's got to go downhill, right? And we want our time to be 1.5 seconds, right? So that information is going to determine our acceleration, right? So the equation that you want to use to solve this guy is this. We know everything in that equation except for A. So plug your numbers in, do your algebra, and find your acceleration, and it ends up being negative 2.44 meters per second squared. Almost. Everybody good up to there? All right. So we just found, bless you. We just found the acceleration. What should we do? Multiply by the mass to find the net force. Good. That needs to be like knee jerk. Oh, I got the acceleration. What's the net force? Or, oh, I got the net force. What's the acceleration? Is it 30 kilograms still? Is that right? Oh, I can't remember that. You get a net force of negative like 73.214. Sorry? 73.
Okay.
Sorry. But that just made it worse. All right, are we good? All right, now, up here, we got to add some forces. So Roy's going to make the box move down the hill. So there are two more forces that I haven't drawn yet. One of them I know. So which force do I know? Do we use static or kinetic?
Kinetic.
Yeah, we got to jump to kinetic here because the assumption is he's got it moving. I don't know if "got" is a word, but he's made the box move, right? And so now that it's moving, kinetic friction is working against that motion with a force of, is it 106 point something? Thank you. All right, and then there's one other force, namely that of Roy, right? Now, here's the weirdness. Check it out. If Roy, once he gets it moving, if Roy doesn't touch it, it's already going to accelerate down the ramp, isn't it? Like, once he gets it moving, he needs that extra oomph to get it moving. But once it's moving, there's more gravity than friction, so it's going to move down the ramp. Is it going to do it in 1.5 seconds? I don't know. All right, so I'm not going to draw Roy's force again, because I don't know which direction it's going to be in. I think you can fairly safely assume that it's going to be down the hill here, but there will be times when that's not true. okay? Where the ramp will be so steep that Roy needs to sort of work against the pull of gravity to slow it down, okay? So let's do the math. So here's our last step. I know that net force is going to be Fg parallel plus my force of kinetic friction plus my force of Roy, right? And I skipped the other two forces because they cancel out, right? The two perpendicular guys. All right, let's plug in our numbers. Let's see, our net force is negative 73.214. Our Fg parallel is negative 124.25. Our kinetic friction is 106.58 plus the force of Roy. And algebraify it. And when you do the algebra, the force of Roy ends up being negative 55.54, I think. Yep. And what's the significance of the negative? It tells you that he's pushing down, which is we knew, but I just wanted to be sure. All right, and now I can put that in my car. Cool? Questions, you guys? How are we doing? Manageable? A lot of numbers to keep track of, right? Okay. I think unless you guys have questions, I'm done. Okay, so that gives you almost 10 minutes. Well, not really. When do we get out? Oh yeah, we get out at 53. So yeah, you guys have 15 minutes. Awesome. You rocked it. All right, so you guys have 15 minutes. Please use the time to get started on worksheet 5.3b. All right. Oh, sorry, wrong class. What are we on? 4.2. Sorry. Oh, yeah. Thank you. Thank you for reminding me. All right, let me stop. Oh no.
It's up on their
Oh, here it is. I do not mind.